Welcome to the High Voltage AI Podcast. This is Alex Reed.
And I'm Emma Quinn. It's great to be back.
We're continuing our week-long deep dive series this week, pulling from the PXRD newsletter on Substack.
That's right. The whole series is really focused on helping electric utility engineers get up to speed on overhead and underground construction types, why we use them, what they're good for.
Exactly, and we've covered some ground already. On Monday, we talked about that data center tsunami, how it's hitting, 75% of utilities?
Yeah, a huge number. And then yesterday, Tuesday, we looked at the grid impact, how consumption might jump from maybe 4% today to 15% in just 6 years, mostly because of these huge loads.
Huge is right. Which brings us to today, Wednesday. We're diving deep into the technical side.
We are. Today's focus is distribution design when 50 megawatts becomes normal. This is really where the engineering challenges start to bite for utility folks.
Yeah, this is where theory meets reality. We're going to unpack what it actually takes to engineer for these hyperscale facilities and, frankly, why the old ways just aren't working, sometimes spectacularly so.
It's fascinating, isn't it, how utilities are literally having to rethink everything. You mentioned spectacular failures.
Yeah.
Take Pacific Gas and Electric. They had this early request, 75 megawatts in Silicon Valley.
Right.
And their first thought, okay, simple math, 5 parallel 12.47 kilovolt feeders should work.
Seems logical on the surface. 5 times 15, roughly.
Exactly. But then reality hit 6 months later, after 3 different design attempts. They landed somewhere completely different. A dedicated 69 kilovolt subtransmission line with the transformation happening right there on the customer site.
Wow. So that parallel feeder idea just completely fell apart.
Completely. Failed on voltage regulation, couldn't get the protection to coordinate, issues with fault current contributions, even just basic reliability. It just didn't work.
That PG&E story, it's more than just one project, isn't it? It really signals this massive shift.
It absolutely does. It shows that these loads we used to think of as outliers, they're now fundamentally challenging how distribution engineers even approach their job.
Yeah.
It's not just tweaking anymore, it's redesigning for a whole new kind of customer.
Okay, so let's dig into that. What are those bedrock assumptions of traditional distribution design, the things engineers have relied on for decades, that are just getting blown up by these 50 megawatt plus data centers?
Well, traditionally, we always assumed single customers would have relatively small loads, 5 megawatts, maybe 15 megawatts max.
It was spread out.
Exactly. Loads were spread across lots of different feeders, and you got this huge benefit from diversity. Not everyone peaks at the same time.
Yeah.
A typical 12.47 kilovolt feeder might serve, say, 200 to 400 customers.
Okay.
Their combined peak might be 15, maybe 20 megawatts. And the load factor, how much energy they use compared to their peak, maybe 60, 70%.
Got it.
Mm-hmm.
So how does one single 50 megawatt data center stack up against that picture? What does it actually do to the grid?
Well, the contrast is pretty stark. First, the load size. One 50 megawatt data center, that's like taking 3 or maybe even 4 entire traditional distribution feeders and giving them to one customer.
Wow, 3 or 4 feeders worth.
Yeah. Second, the load factor. We talked about 60 to 70% for traditional feeders. Data centers are often running at 95%. Continuous, almost no break.
95%. Okay.
Third, power quality. They need incredibly tight voltage, plus or minus 2%. Our standard distribution systems, we usually design for plus or minus 5%, much looser.
Big difference.
Huge. And finally, reliability. They often demand 99.99% uptime. Standard distribution might be closer to 99.9%. That extra 9 makes a massive difference in design complexity.
So when you put all that together, the load size, the continuous operation, the tight voltage, the extreme reliability, trying to serve that with a bunch of parallel distribution feeders, it really does feel like trying to force something that just doesn't fit, doesn't it?
It really does. You're essentially trying to handle a small transmission level load using distribution infrastructure, and the physics just starts working against you.
Which brings us, I guess, to the core engineering decision here.
Yes. Voltage level selection. Get this one decision wrong up front, and every single thing you do after that becomes harder, more expensive, and more complicated. It's absolutely critical.
Okay, let's walk through the options, starting with the familiar territory, 12.47 kilovolt systems. Traditionally used for loads up to, say, 15 megawatts. Does that ever still work for data centers, and where does it break down?
It can work sometimes for, smaller enterprise data centers, maybe 5 to 15 megawatts, or things like edge computing facilities, especially if there's already spare capacity on an existing feeder, or maybe if the customer is okay with standard distribution reliability.
For the bigger loads, where are the technical walls you hit?
Oh, the walls are significant. Let's take that 75 megawatt example again. At 12.47 kilovolt, that's a current of 3,470 ampere per phase.
Wow.
That requires multiple really big conductors, minimum 750K field, probably several circuits of it. Just managing the physical space for that is tough. And then voltage drop becomes a huge issue. You could easily see 3 to 5% drop at full load without spending a fortune on regulation equipment.
And protection.
Yeah, and protection gets tricky too because you have relatively limited fault current available from the data center itself to help the relays operate correctly. So coordination becomes a real headache.
Okay, just to make it concrete, if you did have a smaller, say, 15 megawatt data center on 12.47 kilovolt, what's a rough design and cost look like?
Sure. For 15 megawatts, assuming a decent power factor like 0.95, your current is around 731 ampere. That's manageable with something like a 336 kcmil aluminum conductor.
Okay.
Voltage drop over, say, 5 miles might be acceptable, maybe 2.8%. Standard distribution protection gear is often okay. Cost-wise, you might be looking at around $800,000 per circuit mile for the line itself,
Right.
plus maybe another $300,000 for the protection and control equipment at the substation end. So total, maybe $1.1 to $1.5 million per circuit.
Okay, so 12.47 kilovolt has its niche, but clearly not for the 50 megawatt plus loads. What's the next logical step up? Where's that kind of middle ground for, say, 15 to 50 megawatts? The source material points towards 25 or 35 kilovolt.
Yeah, that 25 to 35 kilovolt range often hits a sweet spot. It offers some really significant technical advantages over 12.47 kilovolt.
Like what?
Well, first, you cut the current roughly in half compared to 12.47 kilovolt for the same power. That immediately helps with voltage drop over distance. You get much better voltage regulation.
Makes sense. Lower current, lower drop.
Exactly. It also usually enhances reliability because you often have more options for backup feeds or loop configurations at these voltages, and it gives you more flexibility for future load growth.
Okay, let's take an example. Say a 35 megawatt data center at 25 kilovolt. What does that look like?
Okay, 35 megawatts at 25 kilovolt, again assuming 0.95 power factor, draws about 850 ampere. Still substantial, but manageable. You could probably handle that with a 477 kcmil aluminum conductor.
In voltage drop.
Much better. Over 10 miles, you might only see about 1.8% drop. And you'd need more sophisticated protection than standard distribution, likely with communication assistance, but it's well-established technology.
And what kind of investment are we talking about for the utility to support that?
It's a bigger step up in cost. You're typically looking at building a dedicated distribution substation, which could be anywhere from $3 to $5 million.
Okay, a dedicated sub.
Yeah. Plus, another $1 to $2 million for the 25 kilovolt switchgear and the advanced protection systems within that substation. The customer usually handles their own transformers to step down from 25 kilovolt, but the utilities piece, probably in the $4 to $7 million range.
So more expensive initially, but it buys you capacity and avoids the headaches of trying to stretch the lower voltage too far.
Precisely. It's often the right balance for those mid-range loads.
Okay, so that covers the middle ground. But then we get to the really big ones, 50 megawatts and beyond. The source calls 69 kilovolt subtransmission the emerging standard. That sounds like a pretty fundamental change in thinking.
It absolutely is a fundamental shift. Once you cross that 50 megawatt threshold, 69 kilovolt, which we traditionally think of as subtransmission, really becomes the optimal technical and economic solution. You're essentially moving out of the distribution planning mindset and into transmission level planning right from the start.
And the engineering advantages must be pretty significant at that level.
Oh, huge. First, you get transmission level reliability. That includes the ability to design for N-1 contingency.
Meaning the system can lose one major piece, a line, a transformer, and keep running.
Exactly. That's standard practice in transmission. Much harder to achieve reliably at lower distribution voltages for these load sizes. It often means you only need a single 69 kilovolt circuit instead of that mess of parallel feeders we talked about.
Simpler configuration.
much simpler physically. You also get vastly better voltage stability and power quality over longer distances, and accommodating future load growth becomes much, much easier.
Let's use a big example, say a 100 megawatt data center. What's the 69 kilovolt design look like?
Okay, 100 megawatts at 69 kilovolt, 0.95 power factor again. The current is about 881 ampere. Notice that's similar to the 35 megawatt load at 25 kilovolt.
Right, higher voltage, lower current for the same power.
Exactly. A single 795 kcmil aluminum conductor could handle that. And the voltage drop, almost negligible, maybe 0.8% over 20 miles. But you definitely need full transmission-grade protection, usually involving high-speed communication like fiber optics.
And are there different ways to configure the system at 69 kilovolts for these really big loads, depending on reliability needs?
Yes, there are typically three main approaches, kind of scaling up in complexity and cost, but also reliability. The simplest is a radial feed. Just a single 69 kilovolt line runs from a utility substation directly to the customer substation. Cost might be around $1.2 million per circuit mile for the line, plus maybe $8 to $12 million for the customer substation interface.
But reliability is limited, right, if that one line goes out?
Exactly. It's limited by that single contingency. So it's often suitable for loads maybe in the 50 to 75 megawatt range, especially if they have robust on-site backup generation.
Okay, what's option 2?
Option 2 is a loop feed. You build a 69 kilovolt loop, connecting the customer into 2 points on the utility system, usually with a normally open switch somewhere in the loop.
Ah, so you can feed it from either direction if there's a fault.
Precisely. That gives you N-1 contingency capability for the circuit. Costs are higher, of course. Maybe $2.4 million per circuit mile because you often need more line miles, plus maybe $12 to $18 million for the switching stations involved. This is common for loads in the 75 to 150 megawatt range needing higher reliability.
And the top tier, for the absolute biggest, most critical facilities.
That would be a network feed. This involves multiple 69 kilovolt circuits, maybe 3 or more, feeding into the customer substation complex, usually with sophisticated automatic switching. It's the most robust configuration.
N-2 capable, maybe?
Often N-2, yes, meaning it can handle losing 2 major components, but the cost reflects that. You could be looking at $3.6 million plus per circuit mile, and the substation complex could easily be $20 to $30 million or more. This is for those 150 megawatt plus truly mission-critical campuses.
We've really focused on voltage selection, and clearly it's vital. But you mentioned earlier, even with the right voltage, these data centers bring other challenges. Protection was one. How is protecting these massive electronically dense loads different from protecting a typical industrial park or residential area?
It's a whole different ballgame. Traditional distribution protection relies on relatively simple time-current coordination. Basically, fuses blow and breakers trip based on how much current flows for how long. Communication between devices is often limited, and clearing times of, say, 5 to 8 cycles might be perfectly acceptable.
Okay.
Data centers. They demand incredibly fast fault clearing, often less than 3 cycles, especially for faults on the transmission or sub-transmission system feeding them. Any longer, and their sensitive equipment can trip offline.
3 cycles. That's fast.
Very fast. It usually requires communication-assisted protection schemes, often using dedicated fiber optic channels between relays. You also typically need more sophisticated protection, like differential protection for critical transformers and the main feed lines. And seamless integration with the customer's own protection system is vital.
And you mentioned fault current contribution earlier. How does that play into protection specifically?
Right. So unlike factories with big motors, data centers, being mostly electronic loads, don't contribute much current back into the grid during a fault. This can make it harder for utility relays to reliably detect faults, especially those further out on the system or high impedance faults. It affects sensitivity. So engineers need to use solutions like larger ratio current transformers to see smaller currents, maybe modify the standard time current curves for better coordination, use pilot protection schemes that compare currents at both ends of a line, and perform really detailed short-circuit studies covering all possible operating conditions.
It sounds like load shedding coordination must also be a major concern. If you suddenly lose a 50 or 100 megawatt load, That's a big hit to the system.
It's a huge concern for grid operators. Losing that much load instantly can affect system frequency and stability, so there needs to be very careful coordination between the data center's operation, its own internal protection, like undervoltage or underfrequency tripping, and the utility's broader load shedding schemes designed to protect the entire grid during major disturbances. High-speed communication and coordinated control strategies are essential. And then, beyond protection, there's the other non-negotiable: power quality.
Right. The source material kept emphasizing exceptional power quality. You mentioned the plus or minus 2% voltage regulation. How do utilities actually achieve that consistently for such a demanding load?
It takes dedicated equipment. Standard distribution might rely on simpler regulators or just the inherent stiffness of the system. For data centers needing that tight plus or minus 2% band, you almost always need sophisticated load tap changing transformers, often abbreviated LTCs, at the substation.
Okay, LTC.
And maybe supplementary step voltage regulators with advanced electronic controls out on the feeder if it's a lower voltage feed. Switched capacitor banks are crucial for managing reactive power and supporting voltage. And continuous real-time voltage monitoring and automated control systems are pretty much standard. You can't just set it and forget it.
And the other big power quality villain, harmonics. Data centers are infamous for generating them. What's the scale of the problem and how do you fight it?
They are indeed harmonic factories, mostly due to all the switch mode power supplies in the servers and the variable frequency drives often used in cooling systems. You can see harmonic currents that are, say, 15 to 20% of the fundamental frequency for the fifth harmonic, maybe 10 to 15% for the seventh. Add it all up, and the total harmonic distortion, or THD, coming from the facility before filtering can easily be 20 or 30%.
And that distortion causes problems for the utility grid, right?
Absolutely. Those harmonics can interact with the utility's own equipment, especially capacitor banks, potentially causing resonance, overheating, and equipment failures. It can also distort voltage for other customers on the same system. So mitigation is essential. This usually involves installing harmonic filters, either passive ones, inductors and capacitors tuned to specific frequencies, or more advanced active filters that electronically inject compensating currents. Careful placement of utility capacitor banks is also important, as is continuous monitoring of harmonic levels.
One more power quality issue, flicker. Where does that typically come from with data centers, and what are the solutions?
Flicker, those rapid voltage fluctuations that can make lights visibly dim and brighten, can come from a few sources in data centers. Big culprits include the switching operations of their uninterruptible power supply, UPS systems, especially during bypass or testing. Also, synchronizing on-site generators, starting large motors for cooling systems, and even utility capacitor bank switching can contribute.
And fixing it.
Solutions often involve using soft-start equipment on large motors to reduce that initial inrush current, carefully coordinating any switching sequences for UPS or generators, designing the utility feed to have a low source impedance, making it stiffer and less susceptible to fluctuations, and really close operational coordination between the utility and the customer to minimize impactful events.
Okay, this is complex engineering. Let's switch gears slightly to the economics. The source emphasizes looking beyond the initial build cost, focusing on life cycle cost. How does that analysis really drive the voltage level decision?
That's a critical point. Too often, the focus is just on the upfront capital cost. But you have to look at the total cost over the life of the asset, maybe 20 or 30 years. That includes the initial investment, sure, but it also includes the ongoing cost of operating losses.
Those I-squared-R losses you mentioned, the energy lost as heat in the wires.
Exactly. And those losses are significantly lower at higher voltages for the same power delivery because the current is lower. So you need to factor in the cost of that wasted energy year after year. Then there's maintenance costs, which might differ between voltage levels, and critically, the cost associated with reliability, but the cost to the customer if they have an outage, and the potential revenue impact for the utility. And finally, the cost or ease of future expansion.
Can you give us like a comparison example again? The 75 megawatt case, 12.47 kilovolt versus 69 kilovolt.
Sure. So for that 75 megawatt load, the 12.47 kilovolt option, maybe using 5 feeders, might have an initial capital cost of, say, $8 to $12 million. Seems cheaper upfront, maybe. But the annual energy losses could be around $450,000 per year because of the high currents. Over 20 years, considering the time value of money, the net present value of that option might be $18 to $22 million.
Okay. And the 69 kilovolt option?
The 69 kilovolt option, maybe a single circuit, might have a higher initial cost, say $12 to $15 million. But because the current is much lower, the annual energy losses might only be $180,000. So the 20-year net present value could come out lower, maybe $16 to $19 million. That demonstrates how the higher initial investment can actually save money in the long run. And tied into that long-term view, especially with the uncertainty around how quickly these data center campuses might grow, is the idea of modular design.
Right. Planning for expansion without overbuilding massively on day one. What does modularity look like for the transmission or subtransmission systems serving these sites?
It means things like designing the substation footprint and layout for its ultimate planned capacity, even if you only build out part of it initially. It means including spare breaker positions in the switchgear lineup so you can easily add future circuits without major disruptions. Using modular protection and control buildings and systems that can be easily expanded is also key.
And how about on the distribution side if you're using, say, 25 kilovolt?
Similar principles. Designing the feeders with sectionalizing switches allows you to potentially reconfigure or shed parts of the load if needed later. Sizing key equipment like cables and transformers for maybe 120 to 150% of the initial load provides some built-in spare capacity for growth or contingency. And sometimes even designing the system with a potential future upgrade to a higher voltage level in mind if significant growth is anticipated. It's about building in options.
So boiling all this down, if an engineer is faced with these large data center requests today, what are the practical go-to design guidelines that emerge from this analysis?
Okay, let's summarize. For loads roughly in the 15 to 35 megawatt range, the recommended approach is generally a dedicated 25 kilovolt distribution substation. Feed it radially, but with automatic transfer capability to a backup source if possible. Use enhanced distribution protection, definitely designed for N-1 reliability on the transformer's minimum, and include those load tap-changing transformers for power quality.
Got it. And for the next tier, say 35 to 75 megawatts.
Now you really should be looking at a 69 kilovolt subtransmission connection. A loop feed configuration with a normally open tie point is often preferred for N-1 circuit reliability. Use full transmission-grade protection systems. Aim for N-1 on both the circuit and transformers, and definitely include dedicated equipment for voltage support and harmonic filtering right from the start.
And finally, for the real giants, 75 megawatts and up.
For those, you're likely looking at multiple 69 kilovolt circuits, or potentially even stepping up to 138 kilovolt. Network configurations with automatic switching are common for high reliability. You'll need fully redundant protection systems, probably communication-assisted schemes like pilot wire or line differential. The goal is often N-2 contingency capability. And real-time voltage control with active harmonic filtering becomes essential. So the bottom line here for distribution engineers, especially as 50 megawatts plus really does become the new normal, it's crystal clear. The traditional ways of doing things just don't scale up, not economically, not technically.
And this point really stands out, that voltage level selection is absolutely paramount. Make the right choice there, considering the life cycle costs and technical needs, and the rest of the design, while still complex, becomes manageable. Get it wrong.
Get it wrong, and you'll be chasing problems for years. You'll spend millions patching and upgrading inadequate infrastructure, constantly fighting issues with voltage, protection, and reliability, just like that initial PG&E experience highlighted.
It forces a mindset shift too, doesn't it?
Completely. You have to start thinking like a transmission planner, even if the final delivery voltage is technically distribution. These loads demand transmission-level reliability and power quality, period.
So, looking ahead for utilities doing long-range planning, what are the key takeaways?
Plan for growth. Assume that today's 50 megawatt request is just phase one. It could easily become a 150 megawatt campus down the road. Build in that modularity and future capacity. And power quality is not an add-on feature, it's a fundamental requirement. That plus or minus 2% voltage, the low harmonic distortion levels, they aren't negotiable. Design for them up front.
These technical challenges, while significant, seem solvable with the right engineering approach and investment. But that investment points towards potential bottlenecks elsewhere in the system, which sets us up nicely for tomorrow's discussion.
That's right. Tomorrow, Thursday, we're shifting focus slightly to the broader transmission system impacts. What happens when all these data center clusters start triggering the need for massive, multi-billion-dollar transmission upgrades? We'll get into interconnection queues, those incredibly long lead times, and the fascinating trend of data center developers now trying to buy substations before they even secure the land for their facility.
That should be a really interesting discussion on system-level constraints. Today's deep dive really highlighted the dramatic changes happening at the distribution design level. It's a whole new world for engineers. We genuinely love to hear from you, our listeners, about your experiences. Have you been involved in designing feeds for large data centers? What voltage level strategies have you found work best in practice? Share your technical approaches, your successes, your lessons learned.
Absolutely. And if you have any feedback on today's deep dive, questions about the series, or want to share those experiences, please feel free to reach out to us directly. You can email Alex at alex.read.power.podcast@gmail.com.
Or you can email Emma at emma.quinn.power.podcast@gmail.com. We look forward to hearing from you and continuing the conversation tomorrow.